So in this video we're going to look at representing compound linear inequalities. And all a compound linear inequality is an inequality that either has two or more inequalities being combined with the word and, or two or more inequalities being combined with the word or. And there's differences in what those words mean. If we use the word and, we are saying that both statements must be simultaneously true. Both must be true simultaneously in order for x to be a solution. So we're defining the requirements for x to be a solution, and when we use the word and as our connector between two inequalities, we're saying this must be true and at the exact same time this must be true. When we combine with the word or, we're saying x is true if either statement is true. So this is a much more flexible statement when we use the statement or. If this is true or this is true, then x is true, whereas this is saying both things must be simultaneously true. And one of the hallmarks of an and statement is that we can typically write them as a single inequality. So we have -2 and 5 showing up as boundaries, and this is saying x must be less than 5, right? So x must be less than 5, and this is saying x must be greater than or equal to -2. So notice how the inequality is opening towards the x. So if I write my inequality opening towards the x, I get a sequence, I get a three-part inequality where both inequality symbols are opening in the same direction to the right like they would on a number line. You can never have a three-part inequality where the symbols open in opposite directions. This would always be incorrect. 100% of the time that would be an incorrect statement. So I can rewrite a typical and statement into a single three-part inequality 99 times out of 100. In most things that happen in the real world when you're doing real modeling, an and statement can be simplified into a three-part inequality. There are exceptions, but many of them are contrived. So this says represent the inequality graphically and then in interval notation. So graphically, if we think about what's going on, I have a number line, and I might as well write my number line for this one as well at the same time because I'm going to change ink color. So I have boundaries at -2 and 5. So I'm going to write my boundary numbers in, -2 and 5. And then I'm going to quickly swap my ink color over without blowing it, hopefully. Ink color, change it over to black. So x less than 5, that means 5 is a boundary, but it's not included, so I'd write it with an open circle. And greater than or equal to -2 means -2 is a boundary, but because x can be equal to -2, we write that with a solid dot. And then we recognize that to be less than 5, for x to be less than 5, x is going to need to go this way. And to be greater than or equal to -2, x would need to go this way. And up here what we said is that for x to be true, both statements must be simultaneously true. They have to be true at the same time, and that only happens where we have overlap between the two solution arrows. This region here where the solution arrows overlap is the solution region. And this corresponds to x being like this statement where we compacted it into a single statement. X is between -2 and 5. X lives between -2 and 5. So at the end of the day, my and statement can be compacted into a line segment for its representation. And in interval notation, I would just say that for interval notation, I would say x is an element of the interval starting at -2 but including -2 and running all the way to 5. Because of the open circle, there's no equal on the 5. We will use an open parentheses here. For this one, this says, hey, x needs to be less than 5. So we know that's going to be an open circle. 5 is a boundary not included. And to be less than 5, we're going this way. And for x to be greater than or equal to negative 2, negative x can be negative 2, so we'd have that solid dot there. To be greater than negative 2, x would be going this way. And x is true when either is true. In this case, we want the combination of the two arrows. And when we put the combination of these two arrows together, if I bring this guy down here and draw him, I actually get the whole real number line. So this tells me that x is always true. So I don't even need the boundaries to represent this statement graphically. And I just lost my red line there. I would draw the whole real number line. I would, on here, draw in over my number line a line that went infinitely far in both directions, because it's always going to be the case that either x is less than 5 or x is greater than or equal to negative 2. In interval notation, I would just say x is an element of the interval from negative infinity to infinity. So I get very different results when I use an and an or. And a big part of the next few homework assignments will be to distinguish between when you're in an and situation or and or situation. So for this example, we'll keep the black ink for now. I have boundary numbers at negative 5 and negative 7. So I'm going to make my number line graphically and interval notation. I'm going to go from negative 7 is the smaller of the two numbers, up to negative 5. And I'll write both number lines in to begin with, and hopefully not mess up like I did before, from negative 7 to negative 5. Try to change my pen color over without making a mistake. Ink color back. Oh, see, I did it. I made a mistake. Ink color back to red. So for the or statement, remember, this means if either of the two things is true, x is true. So x greater than or equal to negative 5. That would be, because of the equal to, a boundary there. And less than or equal to negative 7. There's a boundary right there. To be less than or equal to negative 7, x can live anywhere down here to be less than 7. And to be greater than or equal to negative 5, x would need to be greater than negative 5. This is the most common situation for an or statement. The most common situation for an or statement, unless you're really contriving the problem, if you're working with application problems, is to get what we would call two disjoint sets. An or situation, 99 times out of 100, represents a situation where x is either here or here, and it's impossible to be both things at the same time. It's impossible to be bigger than negative 5 and smaller than negative 7 simultaneously, but because of the or statement, we're saying x is a solution if x is meets either one of these two criteria. So life is good. Here's the graph, and then in interval notation we would say x is an element of the, let's represent this arrow first, it's going towards negative infinity. So we're going to say x is an element of the open interval from negative infinity that runs all the way up to negative 7 and includes negative 7. And then it skips some stuff. So we do the union to indicate some stuff has been skipped, but we're going to add on some more stuff. So the union with the closed interval, because negative 5 is included, and notice this arrow is running off to infinity. So there is the solution in interval notation. Over here, if I connect this with the word and, which means both statements need to be simultaneously true, whereas or means just combine the two statements into one. Combine them. This means both must be simultaneously true. So we connect it with an and, we still get the same picture. We get x greater than or equal to negative 5. Well, to be greater than or equal to negative 5, you need to live up here. And x less than or equal to negative 7 means I have to live down here. And then you have to ask the question, can x be here and here at the same time? And what we see is that no, we can't, because these two things are mutually exclusive. I can't be bigger than negative 5 and smaller than negative 7 at the same time. So I actually can't graph a solution because there is no solution. This is impossible. This would be like saying you need to be taller than 6 feet tall and shorter than 5 feet tall at the same time to ride this carnival ride. You wouldn't be able to do it. So this is an impossible situation. In interval notation, I would just say x is an element of the empty set. And this is the set that contains nothing, which says there are no solutions for x, or x is the empty set, another way to represent the fact that there is no way to be both of those things simultaneously. So the last example, we have an or statement and an and statement. We'll go ahead and make the two number lines. So I have a number line here with boundary points at -5 and 5. And these are just usually a matter of trying to reason through whether we have a situation that's possible or not. So we have -5 and 5. So x greater than or equal to -5 means, hey, here I am at -5. I can equal -5. Let's change pen color again. Printer options, ink color. Let's take black. So -5 with an equal to on it. So I can be -5 and less than 5 right here. Oops, except it isn't equal to it, so I need to write it with an open circle. So to be less than 5, I would be this way. To be greater than or equal to 5, I would be this way. And then the or statement says put the two solution pieces together, and that is the solution. So what I see is when I put this arrow pointing that way together with this one, I just get every possible number that can happen. I don't need the boundary points. So in interval notation, again, I would just say, hey, x is an element of the interval from -5. Sorry, x is an element of the interval from, we're going from -infinity to infinity. So we're going from -infinity to infinity. The solutions are all real numbers. Over here, I have x greater than or equal to -5. So -5 is a boundary point. It's included because of the equal sign. I put a solid dot. 5 is another boundary, but it's not included because there's no equal sign on it, so I put an open circle. And I think about what does it mean to be greater than or equal to -5? It means I need to go this way. To be greater than -5 means I need to go this way, and to be greater than 5, x greater than 5 means I need to start here and go this way. And the solutions have to be the overlap between the pictures. So to be greater than -5, I go like this. And the overlap's going to start here. So we're going to throw this away and say this boundary point isn't needed. The two solutions overlap only when we get to 5. So the solutions are going to go from 5 to infinity. So graphically, the solutions are going off from here this way. And then in interval notation, we wind up with x as an element of the open interval from 5 to infinity.